Hello students, let's see class 15 on the course linear algebra and differential equations. Today we are going to see the modeling problems using first order linear differential equation and change of variables that will help us to solve a certain linear differential equation. So when it comes to the first modeling problem that we have to see is the mixing problems. And of course, there is also another example in your textbook that you should see by yourself that is about circuit. So let's see the mixing problem as the first modeling problem using the first order linear differential equation. So just like mixing problems is about mixing a certain chemicals with a certain situation. So here is like the statement of the problem. It says, consider the situation depicted in figure 1.71. A tank initially contains V0 liters of a solution in which is dissolved A0 grams of a certain chemical. So a solution containing C1 grams per liter of the same chemical flows into the tank at a constant rate of R1 liters per minute. And the mixture flows out at a constant rate of R2 liters per minute. We assume that the mixture is kept uniform by stirring. Then at any time t, the concentration of a chemical in the tank, which is C2 of t, is the same throughout the tank and is given by C2, which is A at t divided by V at t, because of the mixture is kept uniform by stirring. That's why we have at any time t, the concentration of chemical in the tank is C2T, which is the same throughout. Why? Because of the chemical is kept uniform by stirring. Yes, I will show you the figure 1.171 so that things will be easy for you. Where Vt denotes the volume of the solution in the tank. This is the volume of the solution in the tank at a time t, and of course A at t denotes the amount of chemical in the tank at time t. Just let's see the figure. Here is the figure, just like to make things easy. You see, now this is the figure, which is a mixing problem. And here we have incoming flows in, which is the solution concentration, C1 grams per liter that we have said, flows in at the rate of R1 liters per minute, okay? Here we have C1 grams per liter, which is coming in. Then at what rate? At the rate of R1 liters per minute to the container. And here we have A at time t, which is the amount of chemical here, the amount of chemical in the tank at a time t. And of course, this container has a volume, and the volume is represented by V at t, that is the volume of the solution in the tank at a time t, okay? Because like it is coming in, so the volume depends in time, yeah? When we stay more time, the volume will be big, yeah? It will be big. Now, here we have C2T, that is the concentration of the chemical that we have said, and C2T, here it is actually, which is the same as A at t divided by V at t, which is the concentration, okay? Because it is stirred uniformly. So the concentration of the chemical in a tank at a time t is simply given as C2T. And the solution of concentration C1 here, C1, yeah, is coming in. Grams per liter flows in at the rate of R1, that is R1 liters per minute. Therefore, when the solution of the concentration is flowing out, just we have like C2 grams per liter flows out, and at what rate? At the rate of R2, that is R2 liters per minute. So for the inlet, we have rate of R1 liters per minute, and for the out flows out, this we have at the rate of R2 liters per minute. And imagine the concentration. Here we have C2 and C1, they are different, meaning. Therefore, how are you going to formulate mathematically? That is, a mathematical formulation will directly move into the differential equation. So just like from the statement that we have, we can say this all. The two functions in the problem are what? Vt and A at t. In order to determine how they change with time, we first consider their change during short interval of time. This change in t minutes is what? It is like the short interval of time, change in t, okay? In time change in t, we have what? R1 times change in t liters of solution flow into the tank, yeah, because R1 is for the inlet, R1 times change in t liters of solutions flow into the tank, and whereas this one is for the outflow, we have R2 times change in t liters. Thus, during the time interval, change in t, the change in the volume will be what? The change in volume will be what? The change that is the outflow minus the inflow, yeah? That is R1 change in t minus R2 change in t. You can write it like this, or you can use it just like you can interchange, no problem, will be negative here. So this will be R1 minus R2 times change in t. So this one is what? The change in the volume of solution in the tank. This is important concept. Since the concentration of the chemical in the inflow is C1 grams per liter, it follows that in the time interval change in T, the amount of the chemical that flows into the tank is what? C1 R1 times change in T, that's true. And similarly, the amount of the chemical that flows out will be what? That will be what? Instead of C1, we will have C2, then R2 change in T. Of course, we have it here. Therefore, the total change in the amount of the chemical in the tank during the time interval change in T denoted by change in A is approximately what? Change in A is approximated by C1 R1 change in T minus C2 R2 change in T. Upon taking change in T common, then we'll have C1 R1 minus C2 R2 to mean. This is another important result beside to this. Now, if we divide this equation, that is 1.72, and this 1.73 by change in time, just we'll have change in V by change in T. This is for equation 1.72, and this one is for 1.73. So this will be change in V is here, yeah? Then upon divide by change in T, you will directly obtain what? R1 minus R2, this is true. And change in A by change in T, just like upon dividing this by change in T, yes, you'll obtain what? C1 R1 minus C2 R2 to me. Mind you, here we have what? This is change in V and this one is change in A. Now, here comes like the derivative. These equations describe the rate of change of V and A. These are the rate of changes of V and A over short period of time, yeah? Over short period of time. Mind you, this is short. That's why we are using change in T. But finite time interval change in T, that's why we are using. In order to determine the instantaneous rate of change of V and A, we should take what? The limit of change in T into 0 to mean. Because we have short and finite time interval. But now, in order to determine the instantaneous rate, like this to mean, dV by dt, this is the instantaneous rate of volume with respect to time. You have to change this change in T into 0. It should be what? Very small, infinitesimally small. Okay, very small to me. This is short, okay, or small, but this is infinitesimally small. That's why we are saying about the instantaneous rate. Therefore, instead of changing time, we are going to use what? Dt. Okay, therefore, this will be changed into dt. Change into will be changed into dt. Therefore, instead of change in V by change in T, we are going to use dv by dt, that is instantaneous rate. And it, of course, it will be R1 minus R2, because we have said that change in V by change in T is R1 minus R2. You can see it here. Yes. And similarly, dA by dt will be same as C1 R1 minus A times V R2 dV dA by dt, where we have substituted for C2 from equation 1.71. Okay, that's why we have this one. And since R1 and R2 are constants, we can integrate equation 1.74, this one dV by dt. That's easy, directly. And upon integrating this, it will be easier. Just we can integrate directly. This dV is equal to what? R1 minus R2 times dt. And upon integrating, this will be what? V at t. And this is the same as R1 minus R2 times t plus some constant, okay, C. Or we can say V naught, that is the volume at t is equal to 0, where V naught is the integration constant. So this one is true to mean. We have checked it here. Substituting for V into equation 1.75, that is here, instead of V, we can use this one, V at t. Therefore, dA by dt will be what? Just like R2 over R1 minus R2t plus B naught A, and this is equal to C1 R1 to me. Therefore, this is like the final differential equation, I can say. And of course, this is easy to find the solution, because the differential equation, this can be solved. And we have also the initial condition for this, that at time 0, A at time 0 is a certain quantity A naught. So this is the final model that we use for mixing. But like you don't need like to memorize this formula. Okay, if you are given a certain mixing problem, is possible like to model according to the mixing problem given for you. No need like to memorize this formula. Maybe you can see this example. It says a tank contains 8 liters of water in which is dissolved 32 grams of chemical. Look, a solution contains 2 grams per liter of chemical flows into the tank at the rate of 4 liters per minute, and the well-stirred mixture flows out at the rate of 2 liters per minute. You see, similar to the model what we have observed. The question is, determine the amount of chemical in the tank after 20 minutes. See it. And what is the concentration of the chemical in the tank at that time? So just like, if you want, you can use this formula directly. Otherwise, you can start to model by yourself. I mean, that is easy. So these are the given conditions. R1 is 4 liters per minute, which is here, as given. And R2 is for the outflow, as we have said, and it is like 2 liters per minute. This is also correct. This is correct. And C1 for the concentration is what? Maybe, where is C1? C1 is 2 grams per liter. Yes. And the volume the tank contains of water in which is dissolved 32 grams. Yeah. So the volume at initial is 8 liters. And A at 0 is what? 32 grams. Where is it? Yes. Of water in which dissolved. That's true. So just like for this part one, that is to determine the amount of chemical in the tank after 20 minutes, we must find A at 20, and A at 20 divided by V at 20 is like what? That is the concentration, yeah? The concentration. We have said it is. Therefore, we have said that change in V is what? R1 change in T minus R2 change in T. That's true. And the dV by dt is 2. That is the rate. Yeah, dV by dt. That is the rate. Therefore, upon integrating this dV by dt, V will be what? 2t plus some constant c, and this one, no, This is easy. No. One step down. This one V is what? This implies V at T is 2T plus C. Yeah. But at 8, V at 0 is 8. That is 2 times 0 plus C. Therefore, C is 8, yeah? Therefore, V at T can be written as 2T plus 8, or you can say 2 times T plus 4. That's why we have here. This is true. This is correct. And change in A is like approximated by C1 R1 change in T minus C2 R2 change into, and dA by dt is 8 minus 2C2. Just like you can substitute these values. And we have said that C2 is what? A over B. Therefore, dA by dt is 8 minus 2 times A over B. Why? Instead of C2, we are using here. Therefore, dA by dt is dA by dt plus 1 over T plus 4 times A is equal to A. Now, this is like separable differential equation, I think, yeah, dA. Yes, we can make it A can be taken here, and dt could be connected with T plus 4. Yes, that is, oh no, so this one is linear differential equation, yes, than to separate, maybe will not be separated if we check it. Anyways, like this is linear differential equation, where we can use this one as 1 over 1 plus 4 as our q of x, yeah, for the linear first order linear differential equation, if you remember. Yes, dA by dt, we can make it like this, dA by dt plus q of x, q of t, a, which is equal to q of x. So like this will be what? Just like we are going to use for the integrating factor q of x dx, yeah? Remember, because it is a first order differential equation, and this will be e integration of q of x is what? 1 over t plus 4 dt. Yeah, that's true. And upon integrating, it will be I will be t plus 4. That's true. Therefore, just like this differential equation can be written as d by dt, this is I times A. Therefore, this is equal to I times q of x. Remember the formula that we have seen yesterday, and I is t plus 4 and q of x is 8. And of course, this is easy now to integrate, yeah? Easy to integrate. Upon integrating this, you'll have what? The integration of this is 8. T plus 4 times A is the same as 8 times T plus 4 squared over 2. That is 4 times T plus 4 squared plus C. That is true. Therefore, like A at T will be the same as dividing this by 1 by T plus 4, like this. Should be cancelled. That's why you are here. 4 times T plus 4 squared plus C. Now, just we have to find the constant C, and we have that A at 0 is 32. And upon substituting in place of time 0, 0, just the value of C will be 64, and you can substitute here. Then A at T is 4 over T plus 4 times T plus 4 squared plus 16. Now, the question is what? Determine the amount of chemical in the tank after 20 minutes. Once you develop the formula, just A at 20 will be substituting 20. A at 20. Just like it will be adding 20 here, substituting 20 here, and finally you will obtain a certain number 20. That's it, which is 296 over 3 gram. And now the concentration C2 is like C2 at like C at 20 is like A at 20 divided by B at 20, and we have A at 20 is here, and V at 20 is 1 over 48. Maybe we can see it. Where is b at 20? Yeah, we can substitute it here. B at 20 is 24 plus 2. That is 48. That's true. Yeah. Because you have here. B at 20 is what? 2 times 20 plus 4. That is 48. Which means we can substitute here 48, and this is like the concentration. So this is how to use like the mathematical model to model a certain mixing problems. Okay, please try to see other modeling problems related to electric circuit where capacitors are there and some other parameters are also included. So the second part of today's class is about change of variable, and this change of variable is helpful like to solve a certain differential equation, of course, first order differential equation. Just like now we will introduce the concept of homogeneous functions of degree 0. Then we will see like a certain application to solve a certain first order differential equation. All right. A function f of x, y is said to be homogeneous of degree 0 if f of tx dy is the same as f of xy for all positive values of t for which tx dy is in the domain of f. This is a concept. If this is equal, we say that f is homogeneous of degree 0. And equivalently, we can say that f is homogeneous of degree 0 if it is invariant. It doesn't vary under rescaling of the variables x and y to mean. This example, f of xy is given by this. Now, if f of tx dy is the same as f of xy, which means we can say that f is homogeneous of degree 0. Just like substitute tx and ty instead of x and y respectively, just like this is simple substitution. Here we have t squared and t squared common, and we can cancel out. And upon cancelling out, we will obtain directly f of xy. Therefore, we can say that this f of xy is homogeneous of degree 0. We can say it. And of course, in the previous example that we just seen, if we factor x squared term from the numerator and denominator, then the function f can be written as this way, just like we took out x squared and x squared. So this will be the same as 1 plus 3 y over x minus y over x squared. Then like we can cancel out x squared by x squared for x different from 0. Now f of xy is the same as this function. And we can see that f can be written on a single variable v, where v is like y over x. We can write it like this. Yes, we can say that this is 1 plus 3v minus v squared, 1 plus 4v squared. You see, now we are doing that where v is like y over x. Now we can say that f of xy can be written as what? This is like a function of two variables. Now we change it into function of single variable where v is like y over x. And this is like a sign of the homogeneous of degree 0 to me. So a function f of xy is homogeneous now of degree 0 if and only if it depends on y over x only, which means like this. On v, we can say it like this. So this is another important theorem for the homogeneous of degree 0 to show. Just either we can show this way or we can show in the previous definition way to me. If xy is homogeneous of degree 0, then the differential equation dy by dx, which is equal to f of xy, is called homogeneous first order differential equation. We know that this is first order differential equation, but we add what? Homogeneous for what values? If f of xy is homogeneous. Therefore, this is important theorem. The change of variable y, that is x times v, reduces the homogeneous for first order differential equation, this one, into what? Into what? Into separable equation. That's why we are using the change of variable concept. So the advantage of the change of variable, or the advantage of using change of variable, is like it changes the homogeneous first order differential equation into separable equation. So once we get a separable equation, just it will be easy what? To integrate them in, yeah? You see this one dv is f at v minus b. This one is 1 over x dx. So in order to find f, or like, yeah, just any variable, we can integrate both sides, and it is easy to find the solution to me. So the advantage of using change of variable is what? It is like to change the homogeneous first order differential equation into separable equation. See example. Find the general solution of this. dy by dx is this one. So let's investigate whether this is a homogeneous system. If it is homogeneous, just we can use the change of variable so that this differential equation will be changed into separable. So the function on the right hand side, this one, is homogeneous of degree 0. You can check it so that we have first order homogeneous differential equation, or if so, we can substitute v as y over x, or you can say y is equal to xv into the equation. Therefore, this dy by dx will be what? D by dx of this. Why? Because xv is what? Y. It was y here. Instead of this y, we are using what? xv. For x plus y, this will be what? Like this. For x plus y is what? Y is what? xv over x minus 4xv. Now we can cancel what? X. Therefore, this will be 4 plus y. Yeah, we can make it v over 1 minus 4b. You see? 4 plus v, like this, 1 minus 4b. That's good. This is the same. This is like this, but we can use the product rule for the derivative d by dx of y, which is x times v is, we can use the product. So this is the derivative of x with respect to x is 1. 1 times is v. This is true. And then x times the derivative of v is x dv by dx. Therefore, x times dv by dx, take it this into the other side. And upon rearranging simple algebra, you will obtain this differential equation, and as you can see, this is separable. Yeah, this is already separable. Yeah, because we can put it this part into dv, and x dx will be together. This is easy. You see, upon rearranging, the separable different variables are expressed this way. Now we can integrate both sides. Yeah, integrate. The integration of 1 over x is simply ln of absolute value of x plus c, and to integrate 1 minus 4b times 4 times 1 plus b squared, just you can use the partial fraction method, and upon using the partial fraction method of integration, this will be divided into these terms, then it will be a matter of integration to me. And this one is what? This is arctan, yeah? 1 over 4 times the integration of 1 over 1 plus b squared is arctan of v, and v over 1 plus b squared is like ln of 1 plus v squared, and this one is ln x plus c to me. Now, let's substitute. In place of v, we have to change into the original equation. That is, our differential equation is dependent not on v, but on v over x. Therefore, now we have to use a back substitution. In place of v, we have to use y over x, and here instead of v, we are using y over x. Okay, ln of absolute value of x plus c1. Therefore, which implies that this will be upon simplification, half arctan of y over x minus ln of x squared plus y squared equal to C1 to me. And we can express this result. This is this one into a single and more easy way. Maybe we can use the polar representation, and upon using polar representation, where x is usually represented as r cos theta and y is r sin theta, and r is simply the square root of x squared plus y squared, and theta is arctan of y over x, yeah, because tan x is y over x, yeah. Therefore, substituting these values x, y, and r in this equation, that is in 1.84, will be simplified into half theta minus ln of r squared equal to C1, and this ln of r will be what, 1 over 4 of theta plus C2, just like exponentiating both sides of this equation, it will give you that r can be written as C3 times e the power of theta over 4. Maybe we can use theta C3 as a certain number. Maybe if you want to make it particular spiral, maybe instead of C3 we can use half like this, half. Therefore, it is easy to find the graph of the spiral, because this is a spiral, yeah, and the spiral will be like this, very beautiful, yeah. This is the graph of the logarithmic spiral that we have for the equation of r equal to half e raised theta over 4 for this interval to me. So this is like this. This is the advantage of using change of variable. Finally, we have to use the Bernoulli equation. The Bernoulli equation is the one of the nonlinear differential equation. And of course, this nonlinear differential equation could be reduced into linear equation by using the change of the variables, okay? But this one is non-linear, okay? So this is the general equation of the Bernoulli equation. The Bernoulli equation is dy by dx plus px of y equal to q of x times yn. This is the reason that makes it non-linear, yeah? Especially if n is greater than or equal to 2, it will be non-linear. Yeah, as you can see, if n is 0 or 1, this 1.89 will be changed directly to linear, but otherwise it is non-linear. Thus, for n greater than or equal to, we can reduce it into linear equation as follows. This is a technique that you have to use if you encounter to the Bernoulli equation. You have to change into linear by dividing this equation into y the power of n over y the power of n all. You see, then this will be what, y the power of minus n, this will be y the power of 1 minus n, this will be q of x, because yn will be cancelled by yn. Now we can say that our u of x will be y the power of 1 minus n. Okay, y the power of 1 minus n, that is this coefficient, this part. Okay, therefore, if ux is like y the power of 1 minus n, what is du by dx? It is simple, yeah? That is 1 minus n y the power of minus n dy by dx, the chain rule. Therefore, from this we can say that y the power of minus n dy by dx is the same as what, du by dx over 1 minus n, this one. Let's substitute. This will be y the power of minus n dy by dx will be substituted by 1 over 1 minus n du by dx here. See, we can use it here. We'll use it here. So the differential equation is now changed. The nonlinear is changed into this 1 over 1 minus n du by dx plus pxu equal to q of x. And this one is what? This is a typical linear. This is linear differential equation. If you have like this linear differential equation, it will be easy just to solve the differential equation. And of course, du by dx, if you multiply by 1 minus n, by 1 over 1 minus n, this will be 1 minus np of xu, which is equal to 1 minus n q of x to me. And this is linear differential equation and can be solved for you as a function of x. See an example. Here we have dy by dx plus 3 over xy equal to 27y is the power of 1 over 3. You see, ln x. Because of this is nonlinear, yeah? And this is Bernoulli. Yeah. If it is Bernoulli, what we have to do is we have to divide this thing, the differential equation, by what? By y is the power of 1/3. Yeah. Upon dividing by y is the power of 1/3, this will be 27 ln x, and this will be 3 over x divided by y is the power of 1/3. This will be 2 over 3. That's right. And this will be y is the power of minus 3 dy by dx. Now we can say that our u will be the coefficient of dy by dx. No, we have said that our u is this one. Yeah, y the power of 2 over 3. Then du by dx will be what? 2 over 3 is the power of minus 1/3 dy by dx. Now we obtain this term and we will substitute here. Therefore, just like upon rearranging, du by dx will be like 3 over 2 du by dx plus 3 over xu is equal to 27 ln x. So this is changed. The differential equation is now changed into this one. And if you multiply by maybe by 2 over 3, it will be multiplying by 2 over 3. It will be easy now. Yeah. Then this will be what? Du by dx plus 2 over xu equal to 18 ln x. And this is linear differential equation, yeah? Upon arriving at the linear differential equation, this coefficient will be treated as p of x. Hence, we can use the integrating factor as e the power of the integration of p of x dx, where p of x is what? 2 over x. So the integration of e raised the integration of p of x dx is like x squared. And this will be d by dx of x squared. You will be 18x squared ln x, because we have to multiply 18 ln x by what? By the integrating factor x squared. This is correct. Then this is x squared. Upon integrating both sides, this will be x squared u. That's right. And the integration of 18x squared ln x needs what? Integration by part. Integration by parts. The technique. Upon using integration by parts, you'll obtain this one. Then u of x will be just divided by x squared. You'll obtain this one. And finally, the solution for the original differential equation will be just like y to rise 3, because this is in terms of u, but finally you have to change that. Instead of u, you have to use the substitution that you use y to 2 over 3's power, because we have said that when you use the substitution, we have said that our u is what? Y is the power of 2 over 3. So back substitution is important, and finally you have to write the answer in terms of this one to me. So this is all about the modeling, solving a certain differential equation just by modeling. Plus to that, we have also seen the homogeneous differential equation of order 0, plus the change of variables to solve a certain differential equation, and the Bernoulli differential equation. Okay, all the best.